In this video, I'm going to go over another theory called molecular orbital theory. Okay, so every theory that we learn, they have their own strength and limitation. Okay, so for example, Lewis structure is good in explaining the connectivity between each atom, right, and the structure in general. And when you're looking at Vesper theory, it will tell us about the geometry, the shape of the molecule. And then when we're looking at you know valence bond theory, that's going to tell us about what type of bond that is being formed and how they are forming them, how they overlap them, right? Talk about hybridization. So now when we're looking at molecular orbital theory, it cannot tell us any of those, but what molecular theory orbital theory is excellent of would be it can use to predict the stability of the molecule, whether this molecule would be formed or not, right? And also it can also use to predict the magnetic property of molecule as well. And we are looking at the combination in terms of the whole molecule instead of just one central atom, like what we did in the valence bond theory. Now we're going to look at the whole molecule. So we are not going to get into those property much, but we are going to look briefly in what is molecular orbital theory exactly. And if you are taking organic chemistry, you're going to learn more of this later. Okay, so I'm going to just give you the introduction of what it is. Okay. So the homework that associated with this section would be paper homework 6.3 and 6.4. Okay, so this would be number 7 to 12. So first, before we start, okay, so just let's take a look at the difference between valence bond theory and molecular theory, molecular orbital theory first. Okay, so the valence bond theory, we are going to look at one specific atom. Okay, so similar to my previous video, when we're looking at just carbon or just hydrogen or just nitrogen or just oxygen. Okay, so but when we're looking at molecular orbital theory, we are going to look at the whole molecule. We're going to look at every single atom within the molecule. Okay, so we're going to use all of their atomic orbitals in this theory. Okay, so when we're looking at the combination of valence bond theory or VBT, okay, so you are going to look at atomic orbitals of just one atom, right? Because we're looking at just one specific atom, so therefore atomic orbital would be just from one atom that you combine them together. The result going to yield you hybrid orbitals such as sp3 hybrid orbitals or sp2 or sp3d or sp3 d2, for example. Okay, so but for molecular orbitals, when you combine, you are going to combine atomic orbitals of two or more atoms. If you combine the atomic orbital of two or more atoms together, you are going to end up it's going to result in molecular orbitals or MO. Okay, so this is hybrid orbital come from valence bond theory. Molecular orbital will come from molecular orbital theory. Okay, so they are different. Okay. So the type of combination that we are going to use going to be the linear combination of the atomic orbitals using the wave function. We're going to treat the atomic orbital as the wave function in this case. Okay, so what do I mean by that? Okay, so the easiest way to explain this would be we are going to treat all of these similar to how we treat the wave. If you add the two waves with the opposite phase together, this positive gonna add to this negative. It's going to cancel each other out. This negative will add to this positive. They are going to cancel each other out. So you are going to end up with like no amplitude, right? So it's cancel each other out. So in terms of orbitals that they are overlap, if the orbitals are different phase, you are going to not find any electron around that region. That's what it means here. Okay, so this no node mean this node right here or this no amplitude right here mean the probability of finding electron would become 0. Okay, so that's what it means. This type of combination is what we refer as destructive combination or destructive interference. Okay, so now the opposite scenario would be if you have the same phase combination, the same positive add to the same positive is going to amplify each other. You are going to end up with a higher amplitude of the wave. Okay, so in this case, if you think about the orbitals, when you bring atomic orbital that have the same phase together, they are going to amplify. So that means that region that they amplify, you are going to find the highest probability of finding electron within that region. That's what it means here. So this type of combination is what we call constructive combination. Okay, so I'm gonna use both type of combination. Okay, so and then we'll take a look at what type of bond it will be formed. Okay, so I'm going to start with the atomic orbitals of just the S. Okay, so this come from two different atoms, not just one atom, just two different atoms. Okay, so for example, I'm going to do the energy diagram. Okay, so you need to be able to construct this. Okay, so if you want to, you are welcome to put this in your note card if you want to. So energy is going up. When you're looking at the type of combination, note that constructive combination will always yield the lowest energy, like lower energy than the destructive combination. The reason for that is because it's more favorable process. Okay, so in this case, what I'm going to do is because I'm combining S. Okay, so this would be like if you don't want to do color coded, it would be like positive. We added to positive, or it's going to be negative, add to negative, for example. Okay, and then destructive combination would be the opposite color or opposite phase, right? So it would be like positive versus negative, or negative versus positive, for example. So now when you combine the wave, as I mentioned before, constructive combination is going to amplify each other. You are going to end up having a very high concentration of electron around the two nuclei. Okay, so they are going to share between these two nuclei, making them to have lower energy because they are going to attract to the two nuclei. Right? So attraction is more favorable process than the other type of combination. The type of combination of these, because we still do head-to-head overlap, S orbital will always undergo head-to-head overlap. So you're always going to end up with a sigma bond. Okay, so this sigma bond specifically is the molecular orbitals, sigma bond 1s, because it's derived from the 1s combination. Okay, so this is sigma 1s molecular orbitals. Okay, so if you want to write that down, this is the what we call bonding molecular orbital. Okay, so sigma 1s bonding molecular orbitals. Now, what would the destructive combination look like then? Okay, so you're gonna push these together, you're gonna push them together. Okay, so you're gonna now push them together. But when you push them together, they are going to not want, they're gonna cancel each other out. So therefore, you are going to end up with something like this. Okay, so the part that they cancel each other out, which is this part right here, this is what we call node. This is where you are not going to find any amplitude. Okay, so that means this is going to be the place where no probability of finding electron. Electron will not reside here. That's what it means. The type of combination, because it's still head-to-head overlap, this is what we call sigma bond still, but we are going to indicate with the stars to indicate that this is coming from the destructive combination. The star indicate that this is come from destructive combination. The type of molecular orbital here is called sigma star 1s anti-bonding molecular orbitals. Okay. So on exam, I would expect you to be able to draw me the picture, right? So draw me the picture of the destructive combination of 1s and 1s. This is going to be the picture that you're going to show me. Okay. Oops, sorry. So all right, so next one, I'm going to do 2s and 2s. What would be 2s and 2s then? Well, since 1s and 2s, the difference is just the size, right? They have the same picture, still like the same shape. So therefore, in this case, it would be identical to what we have before, except it would be bigger in general. Okay. Next one, I'm going to do head-to-head overlap of the 2p. Okay, so head-to-head of overlap. So I'm going to use 2px for us to be like, it's easier for us to see. This would represent, let's say, like if you do a charge, where it would be positive wave, negative wave, negative wave, positive wave. You are going to combine the negative together, or you're going to combine positive together. Okay, so they have to have the same phase. If you do that, for the destructive would be the opposite. Okay, so it would be the opposite color. It would be more like if you do positive, negative, this would be positive, negative. So what it's going to yield would be the same phase. They are going to amplify each other. You're going to end up with a higher probability of finding electron there. So this is going to be the highest. Okay, so you pretty much amplify that, right? So amplify that region. So because still head-to-head overlap, so this is what we call sigma 2px bonding molecular orbitals. Okay, so because this is the sigma bond from head-to-head overlap, from what? From the 2px. Okay, so from the 2px. The other one, the picture that is going to result from this combination would be these two are going to cancel each other out. You're going to have a node where these two cancel each other out and the other would be the same. Okay, so this is where you cannot find any more electrons. Again, still head-to-head overlap, so it would be sigma, but we're going to indicate with the stars to tell us that this come from destructive combination. Okay, so this is sigma star 2px anti-bonding molecular orbitals. Next one, 2py. Okay, so I'm going to do side-to-side overlap now with the 2py. Okay, so I'm going to do side-to-side overlap here. So we are going to have the same phase for constructive combination, the opposite phase for destructive combination. You can do plus sign and minus sign, that's fine with me. Okay, so the constructive, those that are the same would add together, they're gonna amplify each other. But remember, this is yield pi bond, right? Side to side overlap always yield pi bond. So that's why the electron density is actually outside the nucleus plane right here. Is outside the nucleus axis. So this is what we call pi to py bonding molecular orbitals. Okay. When you're looking at the destructive combination, it would be the opposite now. Okay, so they are going to cancel each other out. So if you push these two together, okay, so let's say if you push them together, I don't have the same color here. So you are going to cancel the part that they are coming together. So therefore, in this case, it's going to look like this. So this part, this side of the p orbital would be canceled, right? So therefore, you're gonna have a slightly left on the other side. Okay, so this is still side-to-side overlap. So it's going to form pi bond. It will be pi star 2p anti-bonding molecular orbitals. Okay. Next, when you look at 2pz and 2pz combination, side-to-side overlap is going to be identical to 2py side-to-side overlap, okay? It's just a different orientation, okay? So different axis. So same thing, constructive have to have the same phase, and they are going to combine together to form pi 2pz bonding molecular orbitals. And for the destructive combination, it would yield a pi star 2pz anti-bonding molecular orbitals. So what should you expect on exam? Okay, so this is going to be similar to what you will see part of the homework as well. I expect you to be able to draw me the picture of this. Okay, so I might ask you, hey, give me the diagram or the pictures of atomic orbital of 2py side-to-side overlap. Okay, so then you have to like be able to draw this too. Okay, so one is like destructive combination and the other is constructive combination, for example. So I'm going to cover up to just right here for the molecular orbital theory because it's a little bit more complex. And if you want to be able to predict, for example, magnetic properties or like colors or like emission spectra of a substance, you are going to need to take like the 200 series to learn those, okay? Because there will be like molecular orbital diagram that you need to fill out. And with the molecular orbital diagram, so similar to this, but more complex, you should be able to predict either magnetic property or the color of the substance or even like the emission spectra for a substance. Okay. But for this level, okay, so this is all I'm going to teach you, and you just need to be able to draw the diagram, okay? Last portion of this lecture is going to be the case study that we will look at how the structure would determine the property of a substance. Okay, so I'm going to look at carbon. Okay, so we can use carbon as our case study. Okay, so carbons has many has like different type of allotropes. What is allotropes? Okay, so allotropes are two or more different molecular form, okay, of the same element. So for example, carbon, okay, so carbon can have different form. For example, graphite, diamond, or buckyball. All of these made up from just one single element, carbon. The question is, well, if this made of carbon, this is also made of carbon, this is also made of carbon, why they have different chemical and physical property then? Okay, so the answer going to lie in structure of each of those. Okay, so I'm not going to talk about buckyballs much. Okay, so buckyball C60 here, it's just because it's the property of this would be like in between diamond and graphite. Okay, so I'm going to actually omit that. Okay, so we are going to looking at these two. So I'm going to before we look into either graphite or diamond, okay, so we are going to take a look at the benzene structure first because you will see why later. Okay, so let's take a look at the structure of benzene. Okay, so this is the benzene ring C6H6. In order for me to draw the complete Lewis structure, I need to count the number of valence. Okay, so 6 carbon. Okay, that's 6 hydrogen. Total would be 30. Based on the number of bonds right now, we have a total of 24 electron sharing. Okay, so just count those multiplied by 2. So that means we have 6 left. Where would those 6 go to? Okay, so if you do a dot dot, which are the lone pair, you will see that some of the carbon will not have an octet. So therefore, we will need to actually do a double bond. Okay, so these are the double bond that I just arrived from that. So now every carbon now have an octet. Okay, so now we use all the 30 electrons. You might ask me, why do you choose double bond here? Why cannot it be double bond here? Yep, you can do that as well. Okay, so based on our lecture, the previous lecture, these two are what we call resonance structure, right? Because they are having the same order of atom, but they just have different location of electrons. And if you look at these, like if you count the number of formal charges, these two have identical formal charges. So that means in this case, these two are what we call they both are equally important. Okay, so they both are equally important to each other, and these two are what we call resonance hybrid. Okay, so these two are resonance hybrid. Okay, so in terms of hybridization, okay, so each of these carbon are going to adopt sp2 hybridization because this carbon contain 1, 2, 3 electron groups, trigonoplanar. So therefore, it's going to use one of the S and two of the P to undergo hybridization. So that's why it would be sp2. Okay, so it's applied to all of them. So now I would like to recall from the previous lecture. Okay, so because we know that each carbon would undergo sp2 hybridization, so I'm going to draw the diagram that represent the sp2 hybridization of carbon. From what we learned previously, we are going to use the valence electron in carbon to help us to form hybridization. So I'm going to use 2s and 2p of carbon because these two are in the highest n level. Okay, so these are the number of electrons in carbon. So when we do hybridization, because carbon do sp2, so we're gonna use one of the s and two of the p to form sp2. One of the s and two of the p. So total are 3 orbitals. So that's why your hybrid orbital come out to be 3 of them. And the remaining 2p would be the unhybridized 2p. In order for us to distribute electron, we are going to distribute electron all the way to the unhybridized orbital first, okay, before you pair them up. So that would be it. So what does it tell us? It tells us that any single electron in the hybrid orbitals, these are going to form sigma bond, and the one single electron in the unhybridized would form pi bond. So together, this is what it looked like. Okay, so we have each carbon would contain 3 sigma and 1 pi. Okay, so that means this carbon right here, these are the sigma bond that is formed, and that's the pi bond that is being formed. Okay, so that's true for all the carbon. So what would it look like then? So this is trigonoplanar, right? So this is the sp2. When you put them all 3 orientation together, it gives you trigonoplanar. And this one going to do a sigma bond to another carbon. And then another carbon would do sigma bond to another carbon, and so on until you get the ring structure. And then the outside, okay, so the outside, so these are the 2 sigma bonds. So those are the 2 sigma bonds. And the outside, this is going to form head-to-head overlap with hydrogen to form sigma bond also. Now, what about pi bond then, Ami? For the pi bond, I need to rotate it. Okay, so I need to rotate it. So we see it one angle. So now we're going to rotate to another angle. So if I rotate to another angle, the leftover p orbital that did not undergo hybridization, they are going to overlap with another unhybridized p orbital to form side-to-side overlap, forming pi bond. So that's why this one right here would form pi bond to that, right? So that pi bond to that, and that pi bond to that, and that pi bond to that. And because we have 2 resonant hybrid, so you are so this is another structure to show you all together. Okay, so this is the sp2 hybridization. This is unhybridized p orbitals. So you're gonna end up with 3 sigma, 1, 2, 3 for this carbon, and then 1 pi for that carbon. So now if I put them together, okay, so this is going to be the pi bond of one of the resonant hybrid, and this is another pi bond of another resonant hybrid. But in nature, we don't see the static picture like this, right? Because electrons move around all the time. They just keep moving all the time. So in nature, these type of bond, they are not going to be single bond or double bond. They are going to be the average of these. So that's why I call them resonant hybrid. Okay, so instead of having a specific bond length as single bond or double bond is actually not going to do that. It's going to actually be an average of the bond length between those two because the electron are circulated around. Okay, so and the bond length come out to be between single bond and double bond. Okay, so this is what the actual molecule look like. So these are more like a static picture, but in reality, they are more dynamic. So which means all of these electrons would just circulate around that. Okay, so this is what we call the electron delocalized. Okay, so it can move around. Okay, so this is the hybrid structure of those two. Okay, so why do I talk about that? Okay, so this is when we are going to explain how the structure determine the property of the substance. Okay, so if you're looking at graphite, this is the structure of graphite. You probably recognize that the structure of graphite is very similar to benzene, right? The structure that we see before, except that is more than one benzene ring. Okay, so it's several of them. And instead of having hydrogen, now you actually bond with carbon itself. Okay, so it's just a lot of carbons that form similar structure to the benzene ring, which means if you're looking at the hybridization, so this carbon right here would be sp2, right? So forming sigma bond, sigma bond, sigma bond, and then one pi bond. Same thing with this one as well, sigma bond, sigma bond, sigma bond, and then pi bond. So all of this contain sp2 hybridization. Okay, so that means, remember like the resonant hybrid, that means the electron will delocalize. So that means all of this pi bond, it will not be static in one location, but it's just going to move around. So this movement of electron or this electron delocalization allow the graphite to be able to conduct electricity. Okay, so that's why graphite can conduct electricity because of that. Okay, and each of these, because they are hold together with the trigonal planar is flat. Okay, so that means this is one sheet. This is one graphene sheet right here. When you stack graphene sheet together, it's going to form graphite. So this is one graphene sheet, that's one graphene sheet. And these force that hold them together is what we call van der Waals interaction, which you're going to learn it in Chem 122 later. This force is not covalent bonds. This is a weak intermolecular forces that hold between two sheets together. The covalent bond would be that one right there. Okay, so that's covalent bond right there. So this weak bond right here, if you put enough pressure on it, it would allow this weak interaction to break. And this is how you are able to use your pencil lead, right? Because every time you put pressure, you are breaking this bond, you are leaving the graphene sheet on your piece of paper, and that's how you like write, is able to write out, right? So every time you write something, this graphene sheet will be left on paper. Okay, so and because of this, weak interaction also is making graphite to be a soft material as well. Now, on the other hand, if you're looking at diamond, the structure of diamond for carbon in diamond are going to adopt sp3 hybridization, which means all of these are going to hold together in a rigid structure. So they are going to held in place and they cannot be moved. There is no available p orbitals, no available electron to circulate around. So therefore, it's making diamond to not be able to conduct electricity. Okay, and also it will be the strongest material, like natural material as well, because of this rigid structure. Okay, so and because of this rigid structure, causing this diamond to have a really, really, really high melting point, okay, compared to graphite. Okay, so the take-home message of this is that different hybridization, different structure, you are going to end up observing different property of the compound. Okay. And here is pretty much everything for this chapter section, and you should be able to complete chapter homework chapter 6.4 now. Okay. And your exam would be similar to this homework, paper homework.